So that streaming software just crashed and needed to be restarted. Let's see if everything comes back in the same place as it's supposed to. Seems like it. Okay, fine, onwards. So, what we were doing was to take a look at snapshots. How do they work? So we're going to look at snapshots, I guess, from three different views. We have the view of what LuaJIT does with snapshots, how it presents them, which we might want to copy. We have the view of how they look inside the virtual machine source code and the C code, and we have the view of what data do we have in the log that the GUI is operating on. So let's take those one at a time. Let's write a very small example program and run it with LuaJIT and see what it does. So why don't we say function foo, and we'll do a loop for I is 1 to n. We'll call subroutine bar. We don't need to be compact. And then function bar of n will say if n is greater than some big number, then error. Otherwise we'll call it baz. We'll do something similar. A different number just for fun. So we'll then call the top level function with a small number that won't hit any of the error cases. So what we're expecting here is we define those functions. We call the top level one. It's going to do a loop with 10,000 iterations. That's more than enough to get the code compiled. And we're going to expect it to inline this call to bar, which is going to have a guard here. If the guard fails, it's going to have to reconstruct the Lua stack and then go back to the VM to raise the error. It's not actually going to happen, but that doesn't matter. It needs to generate code that's able to do that, which will involve generating snapshots, which will give us some snapshots to look at. Same thing's going to happen down in bar. It's going to enter this function. It's going to need to perform a guard to say that this machine code is specialized on the case where that does not happen. If that guard will be violated, it will need to use a snapshot to reconstruct the stack and go back to the interpreter to run this, but otherwise it will run that in machine code. So, run that in LuaJIT. First, let's just see if it crashes. Yes, attempt to compare number with nil. Okay, we didn't pass the number in there. Try that again. Okay, now it didn't crash. Now, when we compile it in verbose mode, I'm expecting to get one. This will be simple. We get one looping trace. Yes, one looping trace. So everything got inlined. So it starts on line 2. The trace starts here, and it's a loop. So it's compiling those 3 lines, but it inlines that, which gives us this function, and then it also inlines that because it inlines everything. That's the way it works. It's recording individual atomic steps, and you have to go into functions to find the atomic steps, and so everything is inlined. And if we would get IR code for this, then we get that, and this is without snapshots, so it's by default you don't get snapshots. So that's the raw intermediate representation in the format that the LuaJIT provides it. And we want to see the snapshots now. So to get snapshots, we just run with a different argument. We say we want intermediate representation with S for snapshots, which gives us this. So every line here that says snap is a snapshot. How much program doesn't quite fit on one screen here, although if we scroll down a little bit it does. Let's do that. We might need to so what we have here is the IR code, and the snapshot says what we need to do to reconstruct the stack in the way that it's supposed to be, in the same, with the same contents that it would have if we were running the code in the interpreter. So I'm going to put register allocations in here as well, because I think that's a useful detail. So when start from the top, the first snapshot is empty. The first snapshot says that in the beginning we haven't made any changes to the Lua stack. We haven't run any code yet, so we haven't made any changes to the Lua stack. So if we would need to bail out from this machine code, we don't have to do anything. That's what this little stack picture here says. It doesn't. There's nothing going on here. Although, well, it has one value on the stack, which is this, which I believe is saying that we haven't modified anything. There's a value on the stack, but we haven't changed it, so we don't need to do anything with it. And that snapshot applies to all the instructions that follow down to the next snapshot. So that's saying that for these instructions, there's none of these instructions makes any relevant changes to the stack. That's what the snapshot is telling us. Snapshot is saying that if we need to bail out at any point in here, then we're going to have a stack with a value on it, and we haven't changed that, so we don't need to. So I guess we just reconstruct the stack with make sure it's got the right size. I'm not sure. We need to look at the runtime system code to see what it does in that specific case. But anyway, nothing needs to be committed out of registers. If anything bails out here, there's no state that the machine code is maintaining that needs to be committed back to the Lua stack. And the way that bailing out could happen is on any of these instructions that show a greater than sign there. So that's indicating a guard. So any instruction that has this little greater than sign is a guard. It's an instruction that basically asserts some condition, and if that assertion succeeds, then execution continues to the next instruction. If that assertion doesn't succeed, then we bail out of this machine code, and that is either going to transition us to another bit of machine code, which is simple, it's more or less just a branch, or it can take us back to the virtual machine if we haven't generated any special machine code there. It can take us back to the virtual machine, and if it does that, then it will use the snapshot to figure out how to reconstruct the state to get there. So if any of those guards fail, we go back to the VM without changing anything, but then it's different. Then we get this new snapshot. Number 1 that applies just here, is that right? So this must be entering a function, I suppose. So from this point on, and this snapshot only covers one instruction. So for just that instruction there, if this guard bails out, then this is a picture of how we need to reconstruct the stack. So we're going to need to take the result of IR instruction number 3, which is here, which is to say the value in register RBP. We need to pull that out and poke it into the stack at this location. This is actually a picture of the stack. So there's a value there that we haven't touched. We don't need to do anything. There's another stack value there that we don't need to touch. There's a stack slot here that we need to poke RBP into. There's the next stack slot we need to poke RAX into. Nothing there, and then we need to poke the same value from RBP also here. And here I believe it's saying this is where we're constructing a new kind of control frame. So I think the point, what's happening here is that this snapshot here is constructing the entry into the function bar. So what's this guard? This is saying if the guard, if a certain value is more than 100,000, then this guard will fail, and we need to fall back and reconstruct the stack using that stack trace. This is talking about this line of code here. So what we're seeing here is that the the first snapshot where nothing happens is good until we call into the subroutine bar down here. And once we're in here, if this fails, then, and we want to go back to the VM, we need to tell the VM where we are. We need to tell it that we've actually entered this subroutine. So the machine code, it inlines everything. It doesn't really need to keep track of a call stack. It actually doesn't push a return value on a function call or anything like that. Everything is inline. So you're not, when you call a function in the machine code, you just inline all of the instructions, and all of the registers are allocated in a kind of a global way in together. So there's none of this normal calling convention that you would push the return address onto the control stack and then enter the branch of the subroutine. None of that happens in this because everything is inline. So what it means is that if we need to bail out from a subroutine and we need to construct the state that the interpreter would expect, then we need to do a lot of stuff. And that's what the snapshot is saying there. Okay, fine. Now we have a second snapshot. Isn't this interesting? Is there any difference there? Looks like it's exactly the same as the previous one, which surprises me because I thought that these were all coalesced. I thought that unless there's some difference there that I'm overlooking, which I don't see, it seems like this is redundant. Something to wonder about. But anyway, this is the next snapshot makes more sense, right? Because then we go down into the next subroutine as well, into bar. So here we're gonna, down here when we do the test, if our value is over 200,000, then we're down in function bar. So if that guard fails and we want to bail back to the interpreter, then we need to construct the biggest stack. We need to construct the same thing we had up here, and then we also need to tack on, scroll out there a little bit, we need to tack on another stack frame. So we need to update the top stack frame where the trace started, which is in the foo function. Then we need to also create the stack frame for the bar function, which has one variable in it. And then we need to also construct the stack frame for the baz function, which also has one variable in it. And in both cases, that's the same value. So it'll take, it's actually always grabbing this n value that was defined up above. It only gets more complicated if we do this. I don't think it's usefully complicated. If we go down into the looping case, the loop is just going to be another representation of the same code. So maybe, if I would disable loop optimization, then actually everything fits on one screen and it's a bit neater. So, for my own benefit, going back through, in the beginning, we're in our foo function, nothing interesting happening on the stack. We go down, we go down, we go down. Eventually, we get into the bar subroutine, and we want to check the limit on this value. If it's over the limit, then we want to construct a new stack frame, which is going to tack on this extra stack. It's going to update the stack frame that we started the machine code in, and it's also going to want to create this extra stack frame for the inline function that we're inside. Fine, and this looks redundant to me, and I'm a little curious about how they got there. Anyway. Then the next case, when we're going to want to check for the 200,000, then we're down in the next level in the baz subroutine, and if that doesn't work, then we want to bail out a bit more there. And I guess something we don't have anywhere there, we're not seeing everything that you can see in stack frames here, so in snapshots here. I know that you can also, it can also express when you need to poke a constant in somewhere. So here we're taking values basically out of registers, but it doesn't have to be out of registers. You can also do constants and that kind of thing. So anyway, we're not seeing everything there, but that's snapshots in a nutshell. So how do they look? How do they look in the, take it a little bit out of order, shall we? No, we'll look in the virtual machine source code next. Now I want to see, how do snapshots really look? And that's probably in JIT. So, when the compiler is representing a snapshot, it creates this data structure. This represents one snapshot. One snapshot, okay, and a snap entry. I haven't looked at the exact encoding. Always in the JIT, the encodings are pretty tight and compact and detailed. So we've got our snapshot and we've got our snap entry. We can look at snapshot again. Snapshot entries. How are they encoded? We have some tags here. The snapshot entry is a 32-bit number. And I suppose this is either a reference to the IR. Here's the macro that constructs snapshot. We take a slot number, we shift that left 24, so we got an 8-bit slot number, position in the Lua stack, presumably. And we've got our flags, which says if this, how should we interpret this? Is this something that doesn't need to be restored? Is this a continuation frame? And we've got a ref, which then is going to be this, where did we have it? That's a ref. And how are these represented? If we go into GC trace, we have a snapshot array and a snapshot map. I haven't dug into the meaning of how these are encoded yet. That's going to be one of the first things to do. Number of snapshots, number of snapshot map elements. So what I want to see, so what is a snapshot map? The snap map is snapshot entries. Alright, so we're going to need to understand the exact encoding scheme and compression scheme for these snapshots, and for that we might need to look at the code that actually constructs these data types. But just before we do that, I'm going to pull up the GUI and see what information we actually have in the log here. So, previously we selected a block of machine code, a trace, and we can get a nice high-level representation. We can get the IR listing, and there's no presentation of snapshots here. But if we pick the dwarf level, then now we're seeing kind of the raw data that comes into the user interface. So, I mean, this looks like this graphical user interface might look like a wimpy high-level piece of software, but it's basically working the same way that GDB does. So the logs that it loads are raw binary data structures captured out of the JIT, and it decodes them using dwarf debug information, the same as GDB. So this is a raw C struct as the front end understands it. It's a struct GC trace. So if we hop over to the C source code, we can see the same. I mean, so here's the data structure defined, and here is an instance of that data structure that arrives in the front end. And the way the whole graphical interface works is to look at all of these individual fields in the kind of incredibly low level representations and then construct something higher level. So when we look at a nice high level thing like this is completely constructed from low level data like this, and all of the, you know, like the opcode names and all of that kind of stuff is also pulled out of the dwarf debug information to match up, you know, numbers with symbolic constants and all of that kind of thing. So what do we have in here? We have snapshot there, and if I click this little thing I can chase that pointer. So that's how in the graphical interface, if you have a field that says a pointer to a snapshot, then you can click that and it will go and find that. So here we got a snapshot, have the values of its various fields. End slots is 2, top slot is 9. And we also have this snap map. Maybe we didn't, maybe not catch that pointer. So if I can't expand that, it might mean that the log didn't contain this address. So every time we log something from the JIT compiler, we can figure out which memory we're going to include. And it's possible that we're not grabbing the stuff. I'm just going to look here, just compare the addresses. I need to have a closer look, and maybe it's time to do that now. So what we need to do now is understand the encoding of snapshots. Right. So let's look at the code that constructs them. Well, let's look at the header for the code that constructs them. Snapshot add, snapshot purge, shrink. I want to say that's a register to stack pointer map, we'll see, and replay, restore. Okay, so this module LJ snap is apparently going to let us create the snapshots and also actually operate on them. Let's look at the code. What we got here? A humble 800 lines of code. Nice. So, start from the high level stuff maybe. What does snap add look like? Add or merge a snapshot. And we need to zoom out a bit. So is this the runtime code for reconstructing stack frames, or is it the compilation time code for representing snapshots, or is it both? It's both, but let's see. Add or modified slots to the snapshot. See it here. Yeah, this is operating on IR code, so this is compilation. It seems like this is both. This is and that's really nice actually. Like 800 lines of code is a pretty manageable chunk if that's all it's going to take to construct and compress and, you know, optimize and restore and everything. Add frame links at the end of a snapshot. Give it a JIT state. Map entry map. We need to understand what the map is. Pointer to top slot. How does that work? It loops along the stack, looking for values that are interesting. Loops across the stack, looking for values that are Lua functions, or continuation frames, or C functions. All right. it finds a frame. And setting F top. I don't know how well code reading actually works for this whole live streaming thing. It's nice to get back into live streaming, but this is something you just need to stare at for a while. A little while. Okay, anyway, that's a very low level routine. Take a snapshot of the current stack. How do you do that? You find the region of the stack that you care about. Seems to be the point at which you base slots go back to. Okay, so you get the snapshot entry. This was not a top level function either, sorry, where was the header? Okay, snapshot add. Where is snapshot add called from? A bunch of places. Okay, but it's a nice simple function anyway, so seems like the compiler does some stuff, and it occasionally calls snap add and snap purge as well. And they're kind of pleasing in that they don't take any complicated arguments, right? So at various points, the compiler is calling snap add or snap purge or snap shrink, and it's not passing any special arguments, just the JIT state. Apart from replay there, we'll come back to that one. Oh, interesting. So replay is something that's done. Replay is something that's done when constructing side traces, it seems. So it's possible, but that's not a runtime system thing. That's also a compiler thing. So actually, maybe the restore, that sounds like a runtime part. Anyway, these are the top level functions. These are the ones we're going to look at. So we'll start with LJ snap add. Just takes the JIT state and presumably inspects the state to see if we need. Oh, I'll get ahead of ourselves. Takes the JIT state, gets the number of snapshots, number of elements in the snapshot map, merge, if there are no instructions in between, or if it was requested and there's no guard in between. So just jumping back for a minute. So as I understand it, we're going to very often request a snapshot as our code here. So you know here we had all these, we had one snapshot there, and then we have 11 instructions that all share the same snapshot. So what I would imagine is that the compiler has actually, while it's compiling this, it's called LJ snapshot add probably a lot, maybe even on every single instruction, I'm not sure yet. And then it's come into this routine and it said, do we need a new snapshot, or is the one that we already have the same? And for all these instructions, it said, the one that we already have is fine. And then when it got to this instruction, it said, well, no, now we need a different one. And that's how we ended up with that snapshot being constructed. So I'm expecting to find that logic in here. So I'm expecting to find the logic that makes all of these instructions share the same snapshot here. And I'm also going to look for answers on this one. How is it that we ended up with two snapshots that look exactly the same consecutively? So in my mind, it doesn't make sense to have those two. This one looks redundant. So how did it happen? Is there a very good reason for it, or is it some limitation in this routine when it detects redundancy, or is it actually that there is a difference, we just don't see it in this particular rendering? Either I'm missing it with my eyes, or just that it's not every detail being shown in ASCII listing. Let's have a look for those answers to those questions. So merge. Okay, so for merging, if we have, so if we don't have any snapshots, then we can't merge anything. And what else have we got? And if the instruction referenced by the last snapshot references an instruction, and if that reference instruction is the last instruction we have in the trace so far, am I reading this right? Then, if we are merging, oh sorry, no, hang on, that's an OR, right? Okay, so this is what it's saying, if it's requested or there's no guard. So if we have a snapshot, and I suppose this is what they mean by if it's requested. If the last snapshot is saying that it refers to the last instruction, then we need to look elsewhere in the code how this would happen. But maybe that's how you indicate that you really, really want a snapshot now. You say, well, I've got a snapshot entry here that, yeah, references the current instruction. I don't know. Let's see. That's one case, or if there's no guard in between. Otherwise, if we are merging snapshots, which is an option, and that's very interesting, we might want to disable that and see what code we get. And what do we got here? What is guard emit? So here we have in the JIT state, we have a field called guard emit, and this is a typed IR reference, and if that's not a guard, I'm not sure exactly how to interpret that bit of expression there, but if we look at what is this guard emit, it might give us a hint. Let's get through this little section first, okay? So, okay, this is the precondition for merging snapshots. So we want to add or merge a snapshot if, well, ish. If we have a snapshot that already refers to the current instruction, then that sounds like a trivial merging case, maybe, where you don't really have to do anything. Everything is up to date. Okay. Otherwise, if we're merging and there's no guard in between, so the significance of not having a guard in between is that a guard is the only way that we can ever bail out. So if we make a lot of crazy changes in registers that correspond with things that we're changing on the Lua stack, in principle we need a snapshot to tell us how to reconstruct the Lua stack, but unless there's actually a guard that can trigger that reconstruction, then it's actually redundant. So it's only do a lot of operations on the stack and there's no guards in between, then we don't actually need a snapshot of those until we get to a guard. So we can kind of coalesce a lot of changes together if there's no guards in between, because we never need to bail out at that point and use the snapshot. Okay. But special case, if we only have one snapshot, interesting, if we only have one snapshot, then we're going to init a nop, and we're not going to merge. Okay, fine. So let's see what's the difference between merging and not merging. So if we suppose we don't merge, then we say we have one more snapshot than we did before. Updating nsnap. Whereas if we do merge, and we set, I need to get all of these fields of all of these structures popped into my brain. Okay, I don't yet understand what the difference is between those lines. But anyway, I'm going to zero those fields and go into snapshot stack subroutine. And what is that going to do? Maybe this will give us a hint. This is presumably where the real work is done. Maybe when we look at that, we'll understand why we have those differences up there. Make a snapshot of the current stack. And this is going to call snapshot slots and snapshot frame links. Okay, so I want to dive down to snapshot slots, which is here. Okay. Add all modified slots to the snapshot, and it takes a snapshot entry and the number of slots. And what does it do? It has how many loops? The loop there. It has one loop, add a loop anyway, over n slots. And for each slot, pulls out a typed reference, typed IR reference, is the number of that reference. And then what does it say? If it is slot number 1. Okay, that's a special case. Let's not worry about special cases yet. There's the case where it's a control frame of some kind. Okay, so down here, this should be the simple case. This is when we have an IR reference. I don't think I'll do code reading and live coding again, but I'll turn off right now. Oh. First of all, in RaptorJIT, we don't need this FR2 business is always there. not a continuation of frame. If it is a load, what are we looking at here? Snapshot tag reference. A snapshot entry. An IR instruction. What's the relationship here? Snapshot instruction. You're referencing IR reference. So again, we're looping over the slots. What is the J slot? Back slot map. When do we access that? I want to see recordings. Access. Where is the recording of some specific bytecode? Does this? Not so specific. That looks. Now I'm just trying to understand what is the JIT states slots variable. What does it mean? How is it maintained? This looks like where most of the action is. What is this function really doing? Where it's called from? Oh, okay. Hang on. This only is only debugging code. Okay, so that's not an interesting place to look. Good information. So where else is it? So there is something we maintain. Back slots. Where else? Canonicalized slots. Okay, so is it only in canonicalized slots? That's the function that maintains this, which is a bit more pleasingly small. Canonicalized slots give us just numbers. Let's have a look. Maybe not. A loop over slots. Each slot contains a tagged typed IR reference. If that reference is to an integer, then dereference that to find the actual IR instruction. If it is a slot load and read only, check what that flag means. Flag of the sload instruction. Then we're going to emit a conversion instruction. That's the convert opcode, and convert this typed reference from a number to an integer. No, must be with the result as a number from an integer. And where and why do we do that? Just there. So when we finish recording, look at the function again. When we finish recording, then loop across all our slots. So is this a case where we recorded a trace, everything is fine and rosy and dandy, but we've got some slots containing integer values. The integer type only exists in the JIT, not in the virtual machine, and so we need to make a conversion because we can't have that type. And the way we do the conversion then is to append an instruction at the end, which is here. We're emitting a new instruction to make the conversion, and we're assigning that slot to be the result of that conversion. So this looks like a safeguard to make sure the machine code doesn't let its internal integer type escape into the virtual machine where it doesn't have a proper representation. Okay, fine, but then that's also a little last path. Okay, so the question then is, where are we actually adding things to these slots? Let's take a closer look. Not in check slots. We've already seen that that's just diagnostic code. Not to belittle diagnostic code. I don't see anything there, so let's have a look elsewhere. Okay, so it's accessing the folding optimization, but that's something optional, so that can't be the fundamental bit. Is it just in the snapshot module that we maintain that? Maybe so. There, where we started off, maybe is the fundamental bit. Okay, so where do we add a slot? That's what I want to know. Where do we add a slot here? So that's looping over slots that we already have. That's not what I'm looking for now. Duplicate, no, I want to see where do we put a new slot in. Replay is going to be the one. There's a lot of code there for setting up the side traces. I have an ambition to revisit all of that code because I have an idea for how side traces could be done differently, but it's quite possible that idea is rubbish, and I think that reading this function would be a good sanity check. Anyway, not in there, so where else? Okay, nowhere. So I still haven't found where we are, the kind of generic code. What's the simple case where we add a slot to that structure? Let's have another look. Not going to be in the folder with loop optimizations because they're optional. Just for the moment, I'm actually going to delete that code because I'm tired of seeing it turn up in grep. What's that give us? Canonicalized slots. Yeah, it's not adding anything, that's just modifying the ones that we already have. It's just initialization. It's also just initialization. That. Add all modified slots to the snapshot. So there we already have n slots. So that's reading the slots list. I want to see where we write to the slots list. Well, it seems to be one place. We're writing deduplicate. I mean, if you can have duplicates, you must have put something there in the first place. That looks more like it, but yeah, this is the replaying for setting up a side trace, and that's not going to explain where the slots get initialized in a root trace, which is the simplest case. Through all of those matches, and it's still setting up a side trace. Okay, I don't see it anywhere, so okay, do we need to search header file? No? Okay, I'm going to look at the definition. What is the slot and a base slot? Is it the case that every time is it the case that every time the Lua interpreter would increase, put something new on the stack, that then we update these ones? So is it just base? Yeah, base slot thing. Where do we update base slot? The function call would be updating that. Happen in LJ record. Okay, this is a little bit more like it. Where is that called from first? Okay, so when we're emitting an IR instruction to load a slot, we look at So this is happening when we record. So we want to generate, and it's a tracing compiler. So at the time that we're generating our machine code, we're also following step-by-step actual interpreted execution. So when we want to pick the type for our IR instruction, we can do that based on the runtime value that the interpreter found. So we need to generate this up in the GUI. When we get an sload instruction, where is an sload? Should be some around about in the listing. Okay, so here we have an sload, and we got a type. This is an integer that we get from that sload. Yeah, that's interesting as well. I thought we were saying that we didn't have integers in the. Well, that might have happened separately. Now, another cool thing we can do, incidentally, here is to sort on the opcode. So here we've got way too many instructions to just quickly glance through, but I'm actually interested specifically in sload. So I was looking for an sload instruction. So a kind of handy thing we can do with this tabular view is to sort on opcode, and then scroll down and see all of the sloads in one place. So that's kind of nice anyway. So there's one. I should put the type. Unfortunately, I don't have the type in the textual listing. I gotta add that. So this one loads a function. This one loads an integer. This one also loads an integer. So I think that the code that we're looking at in the C code now is the bit that gives us this type declaration here. So when the JIT generates, when we trace loading from a slot, we're going to generate an sload instruction. We need to say what type we're expecting. We're going to specialize the machine code for the same type that we got when we did the interpretation. So here, this is the value that the interpreter came up with. We're converting its runtime type, is an I type, the tag type, converting that into from the runtime dynamic domain into the compiler, getting a intermediate representation type, and then we're putting that on our sload instruction, and we're setting a flag saying that this needs to be type checked. So then what we get in the compiler, hopping back there, we get an sload like this, which is saying that we're doing a slot load. We expect to get a function, and this number 16, I think I'm not properly decoding it, but that'll be the flag saying that this needs to be type checked. So what we get in the compiled machine code, is a load, and I need to show the machine code here as well, because it's going to load it in and test the type tag to make sure that the value that we got has the right tag, and then it's going to put it into the RAX register in a kind of an untagged form. Now, where were we? Okay, this is some canonicalization. So if the type that we got is a primitive, so if the one that we looked at there, we got a function that's not a primitive, or an integer that's not a primitive, but if we got true or false or nil, those are actually primitives. So in that case, we actually replace it. So we generate that instruction, but then we say, hang on, but did that instruction give us a is that right? Something after, or so we need to do, even if we get a primitive, we need to do the check. Hang on, so do we get two instructions here or one? fine. Okay. So I mean, in this slots list, we're going to need to get constants of all stripes. So when we have a value in there, we're going to want to know if we have a constant or a variable. If it's a constant, then when we restore a snapshot, we can just write the value straight in. Whereas if it's a non-constant, we need to pull it out of a register somewhere, but we're not dealing with that here. Anyway, are we incrementing the slot number here? Or how do we know here? Have a look again here. Ah, okay. So I was wondering how the slots list gets values, and it seems that it happens indirectly. So you have a pointer to the base of the current frame. So when we call a Lua function, we allocate some space on the Lua stack for the local variables and parameters and whatnot, all the stack space that's needed, and then at the beginning of that space we set to base here, and then when we want to fill in values we do it relative to that. So what we're looking for is lines like this for initializing values. It's not references to the J slot field, it's references to the J base field. Fine. And also here we got a variant. You can see the difference between these two. This one specializes the slot on the runtime type, and this one specializes to a specific type. So when we're generating an sload instruction in the compiler, we know what type we want, then we call this, and that's not going to do any assertions. So that presumably if we do that, we need to know that it's right. Ah, okay, no. The caller can set guard in the mode. Okay, so when we call this function, we say whether we want a type check or not. Whereas down here we don't know what type it is in the compiler, so we just want to take a peek at what value the interpreter came up with and use that to decide. That's kind of interesting anyway. So where are those called from? We're learning something. Yeah, this macro sometimes. Get slot JS. If we have filled in that slot, then return that. Otherwise, okay, get tref from a slot. Okay, so we want to get an IR reference to. That's interesting. So we want to get an IR reference to a stack slot, and we don't know if we've accessed that before. If we have accessed it before, then we just return the same one that we had the last time. So this JBase, this is apparently keeping a correspondence between a stack slot. I presume it's correspondence between a stack slot and the IR instruction that provided the most recent value for that slot. With snapshots then presumably tracking that evolution. And anyway, if we don't know what goes there, then we emit this sload. So presumably every time we need to access a slot, we're going to call this, and it's going to emit just the right number of sload instructions without any redundancies, which surprises me slightly. I mean, it makes sense, but it surprises me slightly because I thought we would always just emit sload every time that we want to access a value, and then an optimization pass would eliminate any redundancy there. But it seems like that's done inline, probably for a good reason. Okay, so where is get slot? Whoops, where is get slot called from? Used, should I say, when it's macro? How often? Quite often. Okay, where's simple usage? Okay, so here, function call setup. Function we want to call. Which is okay, we have a function we want to call which is in a bytecode register, which is really an index into the stack. Because the registers are just a portion of the stack. And then we do this get slot on all of the arguments just to make sure that they all have a reference. The funky meta method thing. There's fbase. We have a function referred to in a bytecode register. We are going to get the function value by looking in the runtime stack. We're looking at the value that the interpreter came up with. We're loading that here. It's a tagged value. Then what are we doing? Then we're looking here, not in the runtime stack, but in, I suppose that this is the compiler's representation of the stack. Okay. I've got to sort out in my head where this base is updated. Like, where are we? Actually, how exactly does this does the JIT state base track the Lua state base? Now I have a sudden interest in J base. I'll find the simplest base that's being used. There we have it with the loads. Look at this one more time, even though we already looked at it once. Go to JIT state. We want to return an IR instruction that loads a slot. We're going to look at the runtime value of that slot. And then we're going to poke. Oh, we're going to get the run. No, this is a simpler one if we know the type. Let's see, this is actually the simpler case. We want to load slot. We want to get we want to get a tagged reference, so an IR instruction, typed reference, not tagged, typed, for a reference to this slot with this type and with this mode. So we can say as a caller whether we want any guards. and this is going to emit an sload IR instruction with the supplied type, and first operand is going to be the base slot plus this slot. So the base slot presumably is based on which function we're currently in. So the slot number we've got the base slot for the function we're in, and then this is the slot. So this is, for example, a local variable access. Base slot is where the first space for the kind of activation record. State is, slot is then the index within that. This, and then we poke that into the JIT1. So what the fudge does that mean? So when we load a value, is it the case that every time we load a value while we're recording, every time we load a value while we're recording, we pull the value out, and this is not even getting the value here, right? So this, when we call this, we must be separately actually loading the value, I suppose. Hold on. Where's in simple usage? Not used very much. This is not used very much, but anyway. False. The picture that is forming in my mind is that I wasn't able to verify it, just skipping, hopping, and jumping around there. The picture that's forming in my mind is that when we want, every time we load a slot, like a local variable, from the Lua runtime stack during recording, we also emit an sload instruction, and we also poke that sload instruction into the J slots array to say to just find the mapping where we loaded for each Lua slot that was loaded, which is the IR instruction that does that load, and then that would be half the picture. The other half would be when we modify. Then when we modify a slot, we would want to keep track of that as well. And how would we do that? Where is the bytecode? There is a bytecode that will do a write to a slot. Hang on, let's get a browser window. So I'm starting to see the picture that when we load a value from the stack, then we go to, write this down. When we load a value from the stack, we get the runtime value from JIT states, Lua state space, and we track the compile and load in. Like that. Is it top? I don't remember. But anyway, so we have this mirror image where when we load a runtime value, it gets loaded by the slot number relative to the base for the current function, and when we do that, we we have this like mirror image there where the runtime Lua stack is mirrored in our compiler view of the stack. So we loaded a value. We loaded a value here at runtime, then here we have a pointer to the instruction that does that load, and then if we want to access that value again, you can reference that same instruction. And this is only looking at reads so far, so now I want to see writes. So let's find a bytecode that should do an update, and we'll see what happens. We're going to find a bytecode that would need to change that slots map, that slots array. Okay, so basically everything with a destination operand. So move being a simple one. What's the JIT going to do when we record a move instruction? We're going to have a destination and a variable. It's going to take that and store it there. So what's going to happen to this slots array when we do that? There's one way to find out. Here is the code for recording a move bytecode. What are we going to say? If clear gap method call to avoid resurrecting there. Yeah, doesn't look like much happens here. Interesting. So here we do a move bytecode, and it's just a little bit of sanity checking. It looks like if we're just extending, looks like we're just going to zero stuff on demand. So it looks like actually the recording here of the move bytecode doesn't really do anything. So would we expect then that if we go down to the bottom of this big switch statement, there'll be something that takes care of that, that detects that something needs to get done? Scrolly, 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 scroll. What do we have here? If this bytecode's A operand is a destination, and remove that would be true. If we just executed a bytecode whose A operand is a destination, then assign this looks like the kind of the crucial line here. We're maintaining the current value in our JIT compiler representation of the Lua stack. Hang on, is this JBase? Is that a tref? Yes. So RC must also be a tref then. Where is RC set here? I didn't see that specifically. Hang on, I don't think that our move bytecode, it was not setting RC anywhere. So there must be something generic. Is that up above? RC BC underscore C. Where is that defined? Here. But that is just giving us a number. The BCC, that's just giving us the number of the register, which is to say relative stack slot. Hang on, haven't found our thing we're looking for yet. What is RC then? It's not a TREF. Yes, it is. Hang on, so why is that okay? Are there multiple? Why is it okay? Sign up to a TREF. The BCC is going to be, is RC changed anywhere? I mean, this BCC is going to be a value out of a bytecode. It's going to be a register number, like a bytecode register number that does not have any obvious relationship with an IR instruction number, which is what a TREF points to. So actually that line of code, I don't understand why that's okay. I would have thought that's a type error that we're assigning RC, which is a TREF. I believe we've checked. Yes, RC is a TREF, and yet we are assigning it to a BC reg, I think. And is that just something that C type system allows? How is a TREF defined? As a 32-bit integer. Okay, so that's interesting. Where were we? We were in LJ record. Were we not? We were. This function. And we are wondering, how does RC get initialized? So RC, I think this is a type pun. So that must get corrected somehow, right? So now we've got something that's supposed to be a TREF is a typed IR reference. It should be a IR instruction number with a type tag on the upper 8 bits. But we've got a bytecode register thingy here, so that's not going to work. So we must replace that value and convert it somehow. Okay, and this seems, no, it doesn't happen there. That's only if it's a big value. It's not that. What about here? BC mode C of the op. Okay, now we're getting somewhere. So what kind of operand is operand C for this instruction? If we hop back here, it's a var. Oh no, it's D though in this case anyway. Okay, so the move, it's going to upgrade it. I think. Yeah, there's no B, so it'll take the RC and digressing ever so slightly. In the bytecodes, there's at least two formats of the bytecodes. Let's see if it's in a table there. You can have the ABC parameters, and if you don't need that many, then you can just have A and D, where D is bigger, the size of B and C slots put together. Anyway, now move back. Okay, so it's a variable, which, not B, but C. So we're going to copy a tagged value. we are going to copy a tagged value from the Lua stack. This is loading the value off the Lua stack into RCV. Okay, RCV is going to be the runtime value. And it's also calling this getSlot macro, which we've seen before. GetSlot says, have we seen this load before? If yes, then give that tref, otherwise emit an sload. So in principle that's where our, we're going to get an S load there, but that's not the whole story. So that explains how sorry, that's the wrong line. We were not there, we were here. This explains how RC gets set to an S load instruction, but when we're doing a move, when we're doing this move, then where does that load get turned into a store, so to speak, even though there's no explicit store? Hang on, so we've got to go back down to the bottom here again. A small mental stack overflow. Yes. Yes, 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 yes. Now it all makes sense. So the way that we compile a move instruction is interesting. So we have the bytecode move here, and it's basically a NOP. So this is just zeroing some stuff on demand, but you can think of it as basically NOP, like these ones, like these constants as well. So a lot of bytecode instructions, basically there's no explicit code generation, but there's some implicit stuff. So up above we saw that we have some generic handling that says if the D operand is a variable, then we're going to set the local C variable RC to a tagged IR reference to that value. And I need to think about that as well. If we load a value and then set it and then load it again, how does that happen? Hang on. Figure that out briefly. Have another look at where how getSlot works. Okay, cool. So when we want to get, so this is actually returning the current. Okay, this is much more interesting than I realized. Much more interesting, and answers the question I had before. I was wondering why, when we want to get a slot, why is it that we only emit the S load the first time and otherwise we cache it? I thought, well, why don't we just emit an S load every time, and then emit an S load every time, and then the compiler could detect the redundancy and eliminate them. But the reason is that we might have a new up-to-date version that's been written somewhere, actually. So actually this is not just for the first time it's accessed. This is what we do if we don't have a value already, and we could have got the value either from an earlier load or also from a write. So cool. So anytime we want to access this slot, we get an IR reference to the current value at this location. If that's not initialized, then we emit an S load, and that becomes the initial value there. We see here that gets initialized. And if we already have a value there, no matter how it came about, then that's the current value. So now I can start to see how this is going to feed into the snapshots when we want. Yeah, it's obvious. When we need to reconstruct the Lua stack, we can just go through all of the stack slots that were allocated for the functions that we've kind of inlined, and we can look at what value we have there, and we can see what we need to do. If the value came from a load, then, or if it came from if it came from here anyway, then we don't have to do anything because we haven't changed it. If the value comes from a constant, then if this contains a typed reference to a constant, then we'll just write that constant when we restore the snapshot, and if it refers to any other IR instruction, then we can look there and get that value, suck something out of a register. So that actually makes sense. I don't know if this was any use to follow along. If anybody followed this and actually found it useful, please tell me, because I'm not sure whether live streaming kind of reading new parts of the virtual machine code makes sense. But this was actually very productive in the end. So now I feel that I have a reasonable mental model of how JIT keeps track of the relationship between machine registers and Lua stack slots. And if I just repeat that very briefly, I'll summarize that. We have, in the JIT, we have base. We have two, by the usages. We have the actual runtime stack while we're recording. So when the JIT is recording some code, the JIT state points to the Lua state, which points to the beginning of the relevant bit of the stack, and that contains all of the runtime values. So while we're recording, then we're both interpreting and generating code, and this here refers to the code from the interpreting. This is the actual runtime values, and then we have a mirror image of that in this one, JBase, which says which is this picture for each with a one-to-one mapping here for each Lua stack slot, not what is the value, like the actual value, but where does the value come from, so that then we can fill it in at runtime. So this one might say that the value now is 42, and this one might say that the value is in the register RBX, for example. Or it might say that the value is the constant 42 if it happened to have come from a constant. And this will be done by the typed IR reference, where the JBase points to an IR instruction, and that IR instruction could be constant. It could be anything, right? It could be anything at all. And if it's a constant, then we'll just suck its constant value out and put that straight in the machine code. If it's anything else, we'll look at which register it's in and pluck that, and presumably make any necessary type conversion, since we know the types of all the register values. Cool, done. And take a deep breath and sign off now. Again, if anyone watched this to the end, drop me a mail and say if it made any sense, if this is an interesting genre. Otherwise, I might skip the code reading on the live streaming, but I guess it doesn't hurt anybody. Blah 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 blah. The end.